Okay, we're going to lecture first about the eye. Then the lab, if you notice, it has no set procedure. You're just going to be testing one of the things that I'm lecturing on in the first part. So talking about the eye. No, I am not a biologist. My knowledge of the human body is very limited to the things we talk about in physics. But here is a model of the eye. First things first. What's the purpose of the eye? Simple question with the obvious answer, not some trick question. To give us vision. Sure. So the eyeball is this thing, and of course I believe that God designed this eyeball to do this. That's pretty tricky. So first of all, we have to focus light if we're going to see something. So what have we used in the past to focus light, like right here?
A lens.
A lens. We need a lens, or we could have used a mirror. But God made us with lenses. I saw actually a funny meme yesterday. It was one guy with a Schmidt-Cassegrain style telescope. That's a telescope that has a mirror for its objective. And another guy with a standard refractor telescope that doesn't have mirrors. And the guy with the refractor says, "Ooh, that must be a vampire." The guy with the reflector says, "Where? I don't see him." Good joke, right? For people who know the difference in their telescope designs. Okay, so we need a lens or a mirror to focus. What does our eyeball use? Use what? Do you say Gauss's law?
No,
God's law. Wait, what does our eyeball use to focus? Okay, well, it uses a lens. Now, which lens, what is the primary focusing thing of your eyeball? This is kind of a trick question. It's one you may not know. It's the cornea.
I don't know what she was saying.
So the light comes in, and if you have parallel rays, how far away do you suppose something is if the rays coming to you are parallel? Very far away, approaching infinity. So if your eyeball is relaxed, in theory, you're supposed to be able to focus on something infinitely far away. So we say that the far point is infinity. That's ideal. Because for many of us, it's closer than that. And I'm going to have you do that. That's the thing I'm going to actually add to the lab is measuring your far point and doing some work with that. So we have these parallel rays, and the cornea bends the light and makes them come to a focus on the back of the eyeball. So the cornea is the primary focusing element. Then the next thing it comes to is the aqueous humor. The aqueous humor is a very similar to water fluid that's behind the cornea. Then it has the iris. The iris is, of course, what gives you your eye color. And it has a hole in the iris. The hole in the iris is called the pupil. And what's the purpose of the iris? It's what? It doesn't change the shape of the lens. Something does, but it's not the iris.
It's dilate, constrict.
It's to change the amount of light that you let in. Because in bright light conditions, you can overdrive the sensors, the cones generally, on your eye, and that's not a good thing. And in low light conditions, you want to get as much light in as you can. So we have this iris that will open and close. So in bright light, it's small. In dark situations, it's large. So a number of you, how many people have taken EMT class? Okay, so it's just 3, not as many as I thought. But one of the things you learn to do in the EMT class is to use the iris as an indicator of the person's well-being. What does it tell you when you do the iris test?
It tells you that your pupils are equal and reactive.
Okay, if the pupils are equal and responsive, what does that tell you about the patient?
They're not, they don't have a concussion or brain injury or something.
Yeah, it tells you that their brain is, at least in this aspect, communicating right. If their pupil is blown, if it's just constantly as big as can be, you're like, uh-oh, there is something wrong. Their brain isn't communicating properly. So it's a way of determining how well the brain is working. And then you also go like this. The only way I could ever tell if somebody's drunk, I could never smell it on the breath. Of course, what do you smell on the breath? You don't smell alcohol. You don't know that, right? You smell other things that are in the alcohol. So if somebody is sober, their eyes should just follow it. What do their eyes do if they're not sober? Y'all say, I don't know, because you're
Not follow.
Yes.
Even if you drink vodka, is that still true?
Huh?
Even if you drink vodka, is that still true? Please.
That I can't tell?
No, I mean that.
Because that's definitely true.
Because isn't vodka odorless?
Well,
Vodka's
alcohol
odorless.
itself,
Oh, it's clear.
It's
it's clear, but
definitely
alcohol
odorless.
itself is odorless. Our ENT teacher said, if you ever are called to court, you can never say, I smelled alcohol on their breath, because you can't smell alcohol. You smell other things that go with it. So say I smelled wine or I smelled beer, but not I smelled alcohol. Not that this is important to our physics class. The way the eye works is important, I think. So a normal person, their eyes should just follow it. But if somebody is altered, you move your finger back and forth, and their eyes may do different things, wander about or go like this. Because once again, the brain isn't quite working right when you're on drugs or, on alcohol or whatnot. So we can use that for kind of a mirror into how the brain is working. But its purpose is to control the amount of light that gets to the back of the eyeball. Now, we said that the cornea is the primary focusing element. I should add, I had a couple students whose parents were both ophthalmologists, and they're like, actually, it's that membrane in front of the cornea doing the focusing. And that is true. But the cornea is what gives it the shape. And for our physics class, we just discount the membrane. We get to that lens. What's the purpose of the lens if the cornea is doing the focusing?
Come get it. What's it?
To make the image form on the retina.
Well, the lens, if we're looking like infinitely far away, the cornea should make the image form on the retina. So what does the lens do? And it's not really looking like an onion, it's just what this picture looks like.
It helps.
Isn't it just a focusing agent?
It is a secondary focusing agent that allows us to do what we call accommodation. It allows us to adjust the focus instead of having only focusing on fixed distances away. So the lens accommodates, two M's, right?
Mm-hmm.
So we can focus on nearer things. One? There. So that second lens allows us to focus on near things. Now, those ciliary fibers, there is a sphincter muscle that goes around the lens, and those ciliary fibers connect it to the lens, and that allows us to deform it. So it's a deformable lens. We actually can physically change the shape of that lens with muscles. Then we have the vitreous humor. That's, again, basically the same as water. And then back at the back, we have the retina. That's where we see. And on the retina, we have we have four things fundamentally. We have rods. They give us light versus dark. And then we have cones that give us color vision. The rods are much more sensitive. So in low light conditions, the cones, there's not enough light to see, and you just see black and white. So low light conditions, you don't see colors. I used to keep a big 7-Eleven big old cup next to my bed filled with water. And in the middle of the night, it just looked like it was gray and white. Whereas normal light, it looked red and white. Why? Because in low light, you can't see color. That's why when you're out there looking at stars, they all look white. They have color, but you can't see them because they're not bright enough for you to see colors. And then the fovea is a special place on the cornea. I'm not going to talk about that. Where this disc is, by the way, that's where you have a blind spot. You have a blind spot, a place where you can't see. Your brain just kind of fills it in so you don't realize it's there. But you can do simple experiments like, stare at this finger, put one beside it, and slide it out. And then you'll get to a place where it just disappears, and then you keep going and it reappears because of the blind spot. So I haven't even gone past the first slide. We're talking about the eyeball and how physics relates to the eyeball. So first of all, when we're looking at something, this is an example of a tree, that cornea should be taking the light that comes from the tree. It's all diverging. It's spreading apart as it leaves the tree. Remember, light from the tree is going in all directions. And the light that hits our eyeball has spread some. And then the cornea focuses it back together on the retina. Okay, you got to tell me what's funny.
It's not even that funny. It's the tree's so tiny and the eyeball is so big. Like, what if our eyes were that big? Yeah, with you, Andy.
Okay.
It's not even that funny. It's just amusing. Like, I'm picturing like a titan just looking down, like, yes, my succulents on the planet are growing.
Okay. Glad I asked. So we have light from, and it's kind of funny. This is a great day for me, isn't it? Everybody's just laughing. Light from the tip of the tree should come here too, right? And then if it's the tip of the tree, it's going to go to there. All of the rays from the tip of the tree that go through the pupil, remember the pupil is the hole in the iris, should be brought to focus at one location. So the tip of the tree, everything is here. The roots of the tree, everything is here. And so we have an image of that tree on the retina. And then we have light detectors that say, ooh, I've got something here. So that's how it's supposed to work. By the way, you notice that tree is inverted. That means that we see everything inverted and our brain turns it around. Have I talked about experiments on this? Yeah, they've done experiments where they gave people prismatic glasses that just reversed up and down. And then they had them do things like eat. And they're trying to get it into their mouth because they see it's too high and they lower it. But in fact, when they saw it was too high, it was really too low. So yes, they would have to close their eyes to eat comfortably. But over the course of 2 weeks, they learned to deal with it.
Oh, man.
They were able to ride bicycles and whatnot.
Cool.
But then when you
When
go
they
back,
take
they
off.
have trouble, right?
Yeah, when they took them off, then they had trouble again. So you're learning to interpret differently was the conclusion of this. Whereas with the ears, when they tested hearing and your location of things, wearing prosthetic ears, after a while, they learned to locate things by sound. And when they took them off, they had no problem. They learned a new skill instead of learning to interpret differently, which is cool. Okay, so that's what's going on in your eye if everything is good. What if everything is, skip this. What if everything is not good? What if you have a vision problem? I am glad to see that Anna actually did wear her glasses. Thank you. I was telling Andrew, Anna said, no, not going to happen. But she did it for me. Well, so vision problems. Myopia. Who knows the word myopia?
I hope we got to.
Should isn't the word. Myopia has a much more common name, nearsighted. And so most people with a vision problem are nearsighted. Most people. So the myopic eye, you've heard, that Dr. Webb, he's so myopic. What does that mean? It means I'm short-sighted, that I don't see the future. I'm just like, well, let's fix this problem right now, and I don't know what's going to happen. There's a ramification next week.
Yeah, I don't think that's better.
It's a common, I mean, not referring to me necessarily, but it's. Okay, so myopic people are nearsighted, which means can see near things. Nearsighted is very literal. They can see near things, which of course implies they can't see far things. So if you're nearsighted, you can see things close to your eyeball just fine. It's things that are far that you can't see very well. What causes it? There are two ways of describing it. Either the lens is too strong, which means that it's too curved, too convex, or the eyeball is too long. Either one of those would be a correct explanation. The opposite of nearsighted is farsighted. And farsighted has a name of hyperopia. And so what do you suppose farsighted means very literally? You can see far objects just fine. It's near things you can't see okay. So we need to define another standard human variable. The near point ideal is 25 centimeters. That's what we're going to use. It's not like that's the perfect distance for your near point. That's what's considered standard vision. So what's the near point? It's the closest place that you can focus. So if I want to find my near point, I take a meter stick, put that meter stick so one end is at the same level as my eyeball, and then I move my finger out until it's in good focus. I say, my near point is about 21 centimeters. Ooh, is that better than standard? It's closer, and one could say, yeah, that's better to see things that are closer. What's the ideal far point? Infinitely far away. So let's see my ideal far point. If I move it out here, it's right about there. It's right about the end of the meter stick is my actual far point. That's supposed to be infinite. That's a problem, right? So all y'all are a little bit fuzzy. Not very fuzzy. Y'all look pretty clear to me. If I look back at Jenna, okay, I can't see like her eyeballs. I can see, her eyes, but I can't see her eyeballs. So that gives you an idea of how the vision compares for having a far point of about 1 meter compared to if you can see her eyeballs. Yes, sorry, I did not mean to focus all the attention on you, Jen. So I have a vision problem. Which vision problem do I have? I have myopia because I can see near things just fine, but I have difficulty with far things. So how would we correct for this? Glasses. Okay. This is a true story. It just totally cracked me up. Let's see if I don't have the question right now, but I'm going to tell you anyway. My first year of teaching, I think it was, I had Xilia Xu in my class. He was a Chinese student. And I was telling them that the first known eyeglasses were invented by the Chinese. She got really excited, because, that's my people. And then I made the mistake of asking the question, what do you do when you can't focus on something very well?
You squint your eyes.
You squint your eyes. And then she got really angry because she thought I was using some bad racial stereotype. But I was not, mind you.
I was not.
The first eyeglasses were created by, at least that I've heard, by Chinese, who took slits of bamboo and made little slits so that they could see better. Yeah. Yeah, have you ever noticed something? So in bright light, I see a lot better than I do in dim light. Why is that, you think? What's the difference in bright light and dim light?
There are more light rays bouncing off the fence.
How?
There are more light rays bouncing off. The iris is the key to answer here. With the iris bigger, you have more light that's being accepted, which means that you have a better chance of it not being at one point. If it's focused right, it'll be at one point, but if it's not focused just right, it'll be more blurry. When you have a small hole, it's all going to be close to the same place just based on the geometry. And so if you have a pinhole, you're going to have perfect vision no matter what kind of lens you have. You don't have to have a lens for perfect vision with a pinhole. So if we all just walked around with a sheet of tinfoil with a little pinhole in it, we wouldn't see much because there wouldn't be much light, but it'd be perfect focus. That's not what we do to correct vision problems. Instead, we use eyeglasses. So for myopia, we use a diverging lens. So let me, by the way, you can use these things too for your lab. You can use basically any equipment I have. I should have set these up before, but I wasn't thinking. So I have an eyeball. Eyeball. I have one. There's my light. Parallel rays come into the eyeball. Why parallel rays? Well, because we're simulating somebody looking at something far. So I put lens number 1 in here. That's coming to a focus pretty close to where it's supposed to be. Number 3, the eyeball is what, too short? So that's a vision problem. Lens number 2, now the eyeball's too long, that's another vision problem. So, with myopia, your explanation is either the eyeball is too long or the cornea is too curved, and you get this situation. You can see why they don't have a clear picture because it's all focused here, and they're trying to decode what's here. So what's the correction? What type of lens should I use? One that is converging or one that is diverging?
Diverging.
Why diverging?
Because that'll make it go a little bit further before it meets the focal point.
Okay. There. Now it's back to a focus there. All is well. So the diverging lens helps it to focus. Now we'll work out the math of it and whatnot in just a minute. Let's go to the opposite problem. This one here. Cornea is too flat or the eyeball is too short. What vision problem is that?
Farsighted.
That's farsighted. So what kind of corrective lens do I need?
Convert.
I need a converging lens. So that converges more, and there it's coming to a focus on the retina again. All is well, vision is restored. That's basically what we're doing with eyeglasses. Any questions about that? Seem pretty clear? Okay. Now, what's going on when we put that corrective lens on? Let us suppose that I should have put a blank page in here and I forgot to. Let's suppose I have an object at the ideal position that we can't see. So what's the ideal near or far that we can't see with nearsightedness? Far. So we're going to have an object at infinite distance. And then we have the eyeball here. There's the eyeball. And the eyeball can't focus on anything beyond the actual near point. So here's my actual near point. Or, excuse me, far point, actual far point. And so I'll put for me that my far point is 1.0 meters. Good approximation. So I put a lens in front of the eyeball that is going to take that object and make an image where I can focus on it. So there's my lens. What is the object distance now? From where to where? That is correct. That's the definition, and that's what I'm going to do. So here is distance object. What is the value for that? If you want to be technical, which is dumb, it's infinity minus whatever distance that lens is in front of my eyeball, which for standard we use 2 centimeters. But of course, infinity minus 2 centimeters, what's that approximately equal to? Infinity. So that's why I said it'd be stupid to be technical here. Now, what about the image distance? Where's the image distance? Where is my lens going to make an image? The cornea combined with, well, actually not combined with the lens. The cornea is going to make the image on the retina if it sees an object that is at the actual far point. So the image that this lens is creating needs to be at my actual far point. So I have an intermediate image which becomes the object that the eyeball sees. Now remember, it's an intermediate image. It's not the final image. The final image is on the retina, as Andy said. So I have my distance image there where it's going to create an image so my eyeball can focus on it. So if my far point actual is 1 meter, what is the distance image? Minus 2 centimeters.
Wait, what?
Because the lens is 2 centimeters in front of my eyeball,
Oh, okay.
and my eyeball can focus out to 1 meter, so it needs to be 98 centimeters.
I thought you were saying the value of the distance of the image was negative 2 centimeters. And I was like, that's...
Yeah, that would be wrong. So my image distance is 98 centimeters, except for there's one thing I did wrong. What did I do wrong? It's something that when you see it, you'll be, yes, definitely that was wrong. Which side of the lens is the image on? Is it on the right side or the wrong side? It's on the wrong side, which means it's a negative image distance. It's making what type of image? A virtual image. There's no actual rays coming together there. That's how the rays that went through the lens would have converged if you extrapolated back. So now I can say the power that I need is 1 over the focal length, which is 1 over distance object plus 1 over distance image, equals 1 over infinity plus 1 over minus, I'm going to put it in meters, 0.98 meters. Why did I put it in meters? Because the standard is diopters, which is 1 over meters. And so the power of the lens here for correction would be just a little bit more bigger in magnitude than 1. You know, so like minus 1.02
Yes.
diopters.
Is that after DIOPTER?
D-I-O-P-T-E-R.
So diopter is the unit for.
That's the units for the power of a lens. And a diopter is an inverse meter. So this figure here is something that could come up on the test, having to draw the figure of how we come up with that diagnosis. I'm also going to have you do this. This is the part I'm adding to the lab. I'm going to have you measure your own far point. If it's more than 2 meters, then you'll just call it infinity. If it's less than 2 meters, then you're going to calculate what power you need to correct your vision. I see you taking a picture, so I'm waiting. So that's correction of myopia. You use a diverging lens. It's going to then create a virtual image at the actual far point when you have an object at the ideal far point of infinity. Now, if we shift to the hyperopia, or far-sighted correction, now we have the problem with the near point. So we have near point ideal equals 25 centimeters, or 0.25 meters. And we might have near point actual equals 1.30 meters. I'm just making up a number. So how do you suppose I arrange my picture to figure out the corrective power necessary? Where should I place my object? For the nearsighted, where did I place the object? Actual. No, not actual, ideal. The object was at the ideal far point, and the image was at the actual far point, because it's a far point problem. For farsightedness, it's a near point problem, so where should the object be placed? We're going to put the object at the actual, or not the actual, once again, ideal, wow. Ideal near point. And where's the image need to be for me to be able to focus on it? I can't hear. Not infinitely far away. It needs to be at the actual near point. So I'm going to make an image out here at the actual near point.
How do you know that that's the actual near point?
Well, that's how we calculate. So you measure the actual near point, and you say, if I put an object at the ideal near point, I want to make an image at the actual near point so I can focus on it.
And those are arbitrary close, right? Or in this
What?
those like those numbers actually.
Yes, or you can get what the power is, and you can calculate the other direction. But yes, because it depends on your eye what the number is. But the key is, the whole point of this lens is to make it where you put something at the ideal near point, you can focus on it. So it makes an image at the actual near point, so you can focus. So now what is my distance object? For this example, for all example, what is the distance object? What is the definition of the distance object? David told us earlier. The distance from the object to the lens. So what's the distance from the object to the lens here? "23 centimeters. Because it's 25 to the eyeball, but the lens is 2 centimeters in front of the eyeball. You will see some problems where it says 2.5 centimeters. It depends on where the eyeglasses are placed, what your prescription would be.
Why does it go to the ideal object and not the actual?
Because the object is the actual physical thing you place there. So it's like I brought my finger to I bring my finger to the ideal place, the place where I want to focus, and that's the object distance. And then the image is going to be out here where I can actually focus. So given my numbers here, what is the image distance? You couldn't hear her, but this is what Sarah said. And what do I need to change on that? Well, I need to change it to minus because it's on the wrong side again. What was that, sir? Oh, yes, that is meters because I put 1.28. Yes. 128 centimeters or 1.28 meters. It needs to be negative. So now I can do the power is equal to 1 over focal length is equal to 1 over distance object plus 1 over distance image equals 1 over 0.2, that's a 2, 3 meters plus 1 over minus 1.28 meters. What do I get for the power here? Well, first, somebody, yeah, give me the power, somebody. Anyone? This one's not as easy to calculate as the other one. .6. So we have a power of 3.6 diopters. This is a positive power. Positive power means it's a converging lens. Is it a real or virtual image that it makes? It's virtual because it's on the same side as the object and it's still the same orientation. Yeah, go ahead.
Sorry, like with any of the eye corrections, like it's always going to be virtual, but what about the surgery? You mentioned
I'm going to talk about the surgery coming up. But yes, with both corrections that we've done, you have a virtual image created by the lens that's at a location where you can focus when the object is placed that you couldn't have focused. So we've covered two things, nearsightedness and farsightedness, otherwise known as myopia and hyperopia. There are other issues. Now, can you have both nearsightedness and farsightedness at the same time? Your eyeball can't be too long and too short in the same eye. You could have different eyes. So one eyeball can't have both. But there's another condition that mimics hyperopia. Presbyopia, old person's vision. Presbyopia literally means old person vision. What is old person vision?
where you have both.
Like when the lens is flat.
It's when you buy the biopsy lens.
Okay, you need, originally we had bifocals as invented by Benjamin Franklin. Now we have other options like continuously varying lenses. But the problem is this thing right here, that crystalline lenses they call it, it can get hard as you get older. And as it gets stiff, it won't flex as much. So in the last couple of years, I've started to have this occur. I can't focus as well on close things as I used to because it's getting stiff. So that near point of 21 centimeters, it used to be like 15 centimeters. It's moving out. What were you going to ask about it?
I was gonna say, like, well, because like it's a muscle, has anybody like found a way, like, can you like do something that will decrease it?
One of the things that you're supposed to do to try to prevent this is to practice focusing on far, near, far, near, far, near, far, near.
Right. Oh, I like my eye doctor will tell me if you're doing homework, like you should look at your if you're every 20 minutes, if you're looking at your screen, look away for 20 seconds.
Oh, I knew that.
Well, and they also are making those glasses that like don't lose the blue light, which somehow works. Have you not heard of like?
I've not heard of that, no.
So like, there's like a different type of light or something that comes from the computer. Well, they're calling it like blue light or whatever, which is what causes the headaches that you get after staring at a screen for a while. So they're making like glasses that supposedly block out that type of light.
Interesting. I'm not aware of that. So some people have presbyopia, that stiffened lens, and along with it, myopia. So the stiffened lens makes it so they can't see near things. The myopia makes it so they can't see far things. So you might have this range, from 45 to 50 centimeters is the region I can focus on. If you can only focus on from 45 to 50 centimeters, that's not very good. And so Ben Franklin came up with the idea of bifocal. So if I want to look at something close, I have the correction for near vision if I look down through the bottom part. And if I want to look at something far, I tip my head down, look through the top part, and I can focus on something far. So you have one lens that's one type, one lens that's the other type. That's what bifocals is all about. But of course, if your range was only 5 centimeters, from 45 to 50 centimeters, what if there's something intermediate? What if I wanted to look at Max? He's not close, he's not far. And so then you have trifocals where you have 3 lenses. And from there we have the gradient ones where it is continually changing the focus as you go like this. So you go like this and you can focus really far away, and then you focus closer, closer, closer as you raise your head. It would be, it takes people a while to get used to it, but after a while they're just used to it, and that's how they adjust for distance. Yeah. Okay, woo clap.
Let's do it. I need to see. 'Raise your hand. There's no vote.
Okay, I just opened it so you can vote now. I didn't want to start it too early because two answers so far. 3, 5. Six, 7. Okay, there we go. 8 people. There should be 9 answers actually. Max stepped out. I will take the 8 and run with it. Those 8 people said virtual, and they are correct.
I thought you were about to say wrong, just the way your phone was.
No.
I was like, oh no.
Sadly, my physical science class, they very often are all wrong, and it slays me. So, what? Put your hand down. Okay. Okay. Whether it's correcting for nearsightedness or farsightedness, the lens is making a virtual image that then your eyeball can focus on. She was just denigrating a certain class of student on campus.
Whoa, he doesn't hear that.
I didn't hear that, so good. Astigmatism. Anybody here have astigmatism? Okay, we have a few with astigmatism. You test astigmatism by looking at something like this, and you ask, which line is the darkest? Yeah. The answer should be, if you have normal vision, they're all the same. Now, if I look at it, the ones that are like this look a little darker to me. That means I have a little astigmatism. Just to check, I rotate my head, and yep, it rotates with my head. Why is that? Just to make Ms. Bauermeister crazy. That's the reason we have astigmatism. But astigmatism is when your eyeball is not perfectly spherically symmetric. So it has a slight different focal length for one axis compared to another. So when I look at this and I said that they look darkest at an angle like this, that means that my eyeball's asymmetry, you can either say it's on that axis or this axis if you want. But it has a slight different curvature. So that means that when I go to have a vision test, and this is beyond what we do for a general physics class, the diagnosis of your vision, they would actually test to see what the difference is in the focal lengths in those two orientations, and you would then get lenses that are also not spherically symmetric to counter that. So you basically have a different prescription for one axis as compared for another axis. So bottom line, what causes astigmatism? Okay, a lack of spherical symmetry to the cornea. What causes myopia? The eye is too long. What causes hyperopia? The eye is too short. What causes presbyopia? You're supposed to say stiffening of the lens. That comes along with old age in many people.
She said that just to annoy you.
It's okay. It's funny. That's the point. Okay, so those are our basic vision problems. Now I'm going to talk about some other things with vision, and there's some important things here. So one is correction with surgery. I think it was Claudia asked about surgery to correct vision. It used to be in the dark ages, like when I was in graduate school, that you could have a surgery where you go to the eye doctor and she measures, what the curvature of your cornea is and what your vision is. And then she cuts a little flap of skin and flips it back. And then she takes her scalpel and she goes and slices your cornea in sections. And then she puts the flap back on and sends you home. And you wear dark glasses for a couple days as your eye heals. And then you check and see how well you see. Yes, it sounds barbaric, doesn't it?
It sounds like something that's like, we'll see if you
This is what they did in the late 80s
try with it or
to correct vision. Why would they sit there and slice your cornea so like they cut it like a pie essentially?
So the cornea
So that you can like manipulate it.
What?
so that you can manipulate it and like shape it so in the way that it will actually work.
It's more barbaric than that.
Oh,
They calculate, you should grow this much scar tissue for the slices, and so if we develop this much scar tissue, it should change the curvature this amount, and that should correct the curvature problem.
for me.
Yeah, I was like, boy, I don't know why anyone would want to do that.
let's play tic-tac-toe.
What we do today is a little better.
A little
It's a lot better. It's a lot better. What they do today is the photorefractive keratotomy, where they cut that flap and flip it back, and then instead of taking a scalpel and cutting a bunch of slots in your eye and your cornea, they have a laser that is controlled by a computer that vaporizes. We call that ablation. That's what I got my PhD in, by the way, was laser ablation. I studied vaporizing transparent materials like sodium chloride, sodium nitrate, magnesium oxide, as well as non-crystalline polymethyl methacrylate. They're vaporizing the cornea with a UV laser. The cornea doesn't pass through ultraviolet light, it absorbs it. And so they know I give it one pulse, it's going to ablate this much material. I need to change the surface so it has this curvature. They carefully calculate how much they have to blade everywhere, and the computer controls how much each part of the cornea gets so that it's resurfaced. This here, it's resurfaced immediately. They put the flap back. You go home as soon as the eye drops that made your iris open up are worn off, you're good. And one of the things that always bugs me is that flap. They cut that circle for the flap, they flip it back, or in some cases they may take it off. They put it back on, it just stays there. It's kind of like contact lenses. Initially, it's not really held there. It's being held there the same way as contact, but then it regrows and you're good. Well, that would be a problem. That would be a problem. But that's what they do with the surgery. Now, when they first were doing this surgery, they only did it for people who were nearsighted. Why the hate for the far-sighted people? Yeah, you can't add to it. You can only subtract. And if you are trying to add to it, you'd have to subtract around the edges. But if you make the cornea too thin around the edges, you can have it tear.
Oh, yeah.
But these days, they've got things figured out to the point that they will do corrections for both.
So did they realize that they couldn't do it when they did it on somebody and it didn't work?
No, I think that they were a little more careful in their thought beforehand, not made a mistake and like, well, we'll never do that again.
We tried it on a sheet first, man.
I'm sure they did that as well, but that's okay. Color vision. I have two pictures here because they show you slightly different things. You have rods that are conveniently enough shaped like that, and cones that are conveniently enough shaped somewhat like that. It's really amazing how they got these names. So the rods and the cones are the color receptors we have. So if you look there, the cone, well, the right-hand picture shows you S cones, rods, M cones, and L cones. Let's take a guess. What do S, M, and L stand for? Small, medium, and large. S is for short wavelengths. And so short wavelengths, blue light is short. So I usually call it the blue cone because it's the one that sees best blue colors. M, medium, its peak sensitivity is in the green. And so we usually call it the green cone. And then we have L, long. Its peak sensitivity is actually in the yellow. You can see the one on the left, it has a yellow line instead of a red. We pretty much exclusively call it the red cone because it's the red side of the spectrum. That's the one that's going to dominate with red light. The green one is the one that dominates with green light. The blue one is the dominates with blue light. So how many colors do we see fundamentally? 3, red, green, and blue. Thus, red, green, and blue are the primary colors of light because that's what we interpret for everything. So this projector is putting out 3 colors. It's putting out a red, a green, and a blue. And we get the colors that we see up there by mixing how much red, how much green, and how much blue are present. Now, a lot of people learned a different set of primary colors. What are primary colors you learned? And the funny thing is, I was always interested in physics. I did not learn those primary colors until I was a teacher. Students said, no, that's not it. What? Huh?
Cyan, magenta, and yellow.
Cyan, magenta, and yellow. Cyan, magenta, and yellow are what, as a physicist, I will call the 3 primary pigments. Pigments versus colors of light. Because if you look at, like red shirt, forest green, cyan, turquoise, these colors are made by having pigments that absorb. So on her red, because red is a primary color, it's easy. It's reflecting red, which means it's absorbing everything else. So it's absorbing the other 2 primary colors. What are the other 2 primary colors? No, of light.
Oh, green and blue.
Green and blue. So her shirt is absorbing green and blue and reflecting red. With the pigments are designed to reflect 2 colors and absorb 1. So a magenta is reflecting red and blue, but absorbing green. Cyan is reflecting, cyan is not reflecting red, so that makes it green and blue that it's reflecting. And which one's left? Yellow. Yellow is absorbing blue and reflecting red and green. So those primary pigments are absorbing 2 primary colors and reflecting 1. Or excuse me, they're reflecting two primary colors and absorbing 1. So that's the difference in the primary pigments versus the primary colors of light.
Are red, yellow, and blue actually primary colors for anything? Because I've learned the red, green, and blue, and cyan, magenta, and yellow as additive primaries and subtractive primaries.
Right, because light is additive and pigments are subtractive.
Right, but then in grade school, I'm sure a bunch of us learned red, yellow, and blue as primary colors. But what is that? Because that's not really.
Okay, so what is that? That is because historically it was hard to get pigments that were the primary colors for pigments. Right, if you look at a printer, what are the colors of your printer? Cyan, yellow, magenta, and of course black. because those were primary pigments. But it was hard to get those colors, and so they substituted things that were close. And so they substituted, yellow stayed yellow, but for cyan they substitute blue, and for magenta they substitute red. And so what does that do? It decreases your color gamut. It decreases the number of colors you can actually make. But it's still a pretty good color gamut, right? The reason I have these two pictures, the left one shows relative sensitivities. Your blue sensitivity is not nearly as good as your green and red. But notice the green and red are pretty close together at their peaks, so there's not a lot of differentiation. This here is just showing the sensitivity for all of the rods, or all of the cones plus the rods. Notice the rods, the peak sensitivity for the rods is somewhere still in the green area. But we don't see green light with that because our brain doesn't interpret that as a color. It just interprets it as bright or not bright. And the rods, like I said, they're more sensitive, so you can see dimmer things with the rods, but you don't see colors. Anybody know what this melanopsin is?
No.
The melanopsin is something that detects light that has nothing to do with our vision. But we still have some in our eye. We also have in other parts of our body. And it's part of what tells us if it's light out and helps our body produce melatonin appropriately. So it's not part of vision. I saw that on there and I had to look it up because it's something I'd never run into before. So if you look here at the picture of, there we go. The picture of the cornea there, you notice the cornea looks kind of funny. This is the front side. And the light has to go through all of this nerve stuff before it gets to the rods or cones. And you can see the kind of conic shape of the cones versus the kind of rod shape of the rods. This is one of those things that comes up when you talk about creation and evolution. It has been argued that if the eyeball was designed by an intelligent designer, why would you have the light going through this network of stuff before it gets to the color-sensitive parts? Is that a reasonable question? I don't know.
I'm sure it's a reasonable question. I don't know the answer to that.
Well, so a lot of people who support evolution say, that would be a dumb design. It couldn't have been designed that way. It had to be, developed for another reason that way. Further research actually indicates that the sensitivity of the rods and cones is adjusted very quickly by light that hits out here. And so we actually have a sort of adaptation in the retina for rapid changes in light to make us so we are less sensitive to changes in light. That is, the sensitivity of the rods and cones will change instantly if you suddenly get a bright flash of light, so that you don't have as much saturation of it. And so that then sounds like it was, built for a purpose. Now, intelligent design is not really a valid argument for creation or evolution. It's not a valid argument because you're making an argument based on lack of knowledge, right? Argument of ignorance. I don't see how this works, so it must not be good. That's not valid, right? It can still be good if you don't see how it works. But there's another thing that to me sounds much stronger argument for creation that comes from the eyes. You probably have noticed that virtually all animals have eyes. And there's very strong similarities between eyes across a broad range of animals, not just mammalians or mammals, but eyeballs of all kinds of different things. And if you go back through the geologic record, looking at fossils, you find that at the Cambrian explosion, you have the Cambrian explosion 541 million years ago, when we went from basically little trilobites to having a broad range of species. So it's called an explosion because suddenly you have all these species where you really didn't before. But the eyeballs across all of those different species that appear at the Cambrian explosion are very similar. And evolutionary theory then would demand that, well, that basic structure of the eyeball, the things that are similar across all of these had to have been developed before the Cambrian explosion. Otherwise, they would have developed differently. Which then means that you had to have the development of this very complex organ back in the very primitive developmental stages, which to me sounds like a pretty strong argument against evolution. Now, obviously, there's lots of arguments. This is just one. You don't win an argument with just one. I talked about this a bit. If you have something that appears red, like Andy's shirt, that means it's reflecting red light and absorbing everything else. If it's looking turquoise, then it's reflecting a few colors, right? It's reflecting more than one color because our eyes, turquoise isn't part of the rainbow. Any color that's not part of the rainbow is produced by having more than one color, and our brain interprets the different levels of those colors to get the composite color. So we have three types of cones, red, green, and blue, if you have normal color vision. If you're interested in checking your color vision, I have the, I can't remember his name, whatever this guy's name, plates here that you can look at and figure out if you're colorblind or not. Color blindness is a sex-linked trait, comes primarily in men. But each of your cones can detect about 100 different levels. Now, if you think about on the computer, we usually set our colors to 256, right? We can go anywhere from 0 to 255 for how bright each color is. Now, probably a lot of you haven't played with that. And so the colors you can make on your computer monitor is 256 cubed, because you have 256 settings for red, 256 for green, 256 for blue. Where our eyes can detect about 100 variations for each one. So that means the number of colors we can see is about 100 cubed, or about 1 million. So a person with normal color vision can see about 1 million colors, because you're just taking how much red cone activation, how much green cone activation, how much blue cone activation to get the composite. Some women are true tetrachromats. That means they have 4 types of cones. And with 4 types of cones, they have about 100 gradations in 4 cones to make their colors, which gives them a color gamut of about 100 million. They can see a lot more colors than the rest of us can.
How do you know if you have that or not?
It's a really good question. I mean, how do we know things about the sensitivities? These graphs here, the sensitivities, the one on the left is showing the actual sensitivities. How do we know that? After a person dies, we can dissect the eyeball and we can test and know. But we don't want to dissect the eyeball before you die, right? Obvious reasons. Yep. We'll put it back together, yeah. So they have done a lot of studying on women who are believed to be tetrachromats. And then after they die, they can check their eye and see if they were. And if they were, then they have valid information about the vision of the tetrachromats.
So there's no such thing as like try.
Well, a problem with the whole tetrachromacy testing is you're not exactly sure what they can and can't see, right? Because we most of us just have the tricolor vision, and so it's kind of hard to figure out what they can and can't see. But after the dead, you examine their cones and look at the sensitivities, and they should have seen this, this, and this. And so it's just an interesting thing. You're not going to be asked about tetrachromacy. You'll be potentially asked about trichromacy, the 3 colors, and how that works. Okay, a couple more questions. What are the primary colors of light? Select the ones that are correct. Oh. Okay, we're done. Here's what we got. 10, 0, 2, 8, 10, 0, 0. Well, the majority is right. Yellow is not one of them, but they are blue, green, and red. Why are they red, green, and blue? Well, because we have one cone that's most sensitive in red cone. That would be the red one would be the L cone. One that's most sensitive to green, that'd be the M cone. And one that's most sensitive to blue, that'd be the S cone. So that's why those are the primary colors of light. It's not any other reason. Now, light sources. I don't have enough of these in the classroom right now for everyone. But if you want to play around, and I will use these in class later, so you'll play around with these later in class. We can wear these and it breaks light up into its individual colors. And so if we look at the light, and what works best for me is actually looking at the reflection of the light off of the vents. I see a red vent, then I see a faint yellow vent, then I see a green vent, and then a light blue vent, and then a indigo vent. That's because the lights in this classroom are not giving us a continuous range of colors. They're giving us peaks as illustrated here. That's the indigo one I saw. And this one here is the light blue. And then we have green and red. So it looks like white lights, but it's this funny relationship. The sun puts out this thing here, that funny shape. And if you use an incandescent light bulb, like the bulb that is being used to light this up, it's a hot piece of metal. It's putting out something like this that has a whole lot more red than it has blue. Now, we haven't talked carefully about the visible spectrum. 750 nanometers is about the longest wavelength that our eye can see. 750 nanometers. 750. And 400 nanometers is about the shortest our eyeball can see. You'll see different ranges written for the human eye because it just depends on where you want to make your cutoff. The reason I make my cutoffs 400 and 750 is because we know frequency is equal to the speed of light divided by wavelength. And so if I have red, divide that by, red is 750 nanometers. That equals 4.0 times 10 to the 14th hertz. And of course, if that's the case, then the frequency for blue or indigo, I'll put blue, so the reason I use 400 nanometers and 750 nanometers, it's a fair setting and it makes it so the frequency range is 4 to 7 times 10 to the 14th hertz. So it's easy, you don't have to learn a different set of numbers for wavelengths and frequencies. You just have the same basic. The eyeballs really are amazing. The eyeballs have edge detection built in. So this picture here, this picture right here, is built using intensities that are stepped up at a constant level. But your eyeball accentuates the edges, so you see these edges strongly. That's actually the reason why you have a lot of funny optical illusions. Like you'll have a picture that has a checkerboard and asks you to compare this black box to this white box. And it turns out they're the same. It's just one of them is surrounded by black, so it looks light. The other one's surrounded by light, so it looks dark. Because of the way the eye adapts. Also, the eye adapts, and you probably noticed this like if you ever saw Jurassic Park. I know it's old now. But we also are good at detecting motion, at changes. So something that's stationary is a lot harder for us to see than something that's moving because our eye picks out the changes. Final thing I'm going to talk about is dispersion, spreading light up by color. Now, I'm using these. We call them diffraction gratings. That's a topic we'll talk about after we get back from break, if we come back from break. We probably will. It's just the college is preparing for the possibility. They're going to tell you to make sure you take home with you all of your books and study materials. So if we don't come back after break, you can still participate in your classes.
Are they gonna just not let us back?
It's still not determined. They just told us at the faculty senate today, and they said they're still working out exactly what it will be. And somebody said, but you got to tell them soon because some people aren't going to stay until it's time to go. They're going to leave early. But I will still lecture and put the lectures on YouTube and put homework up if you know. Huh? I haven't thought about that yet. I guess I should because we've been charged for the last 2 weeks or a week and a half to figure out how we're going to teach classes if we can't come back. What was that? Give you the answers? Huh? No, I don't think it'll happen either. But we want to be ready. There's a couple of universities that have already gone this route. Amy was saying Ohio State University and Harvard have already.
There's a large list of them now. It's getting larger.
A large list of them. Well, you know Union College is going to jump on board. We can't get left behind. Plan for a big... Okay, remember, what happened during the Black Plague? Well, okay, there's that. But they canceled school. Isaac Newton went to his grandma's house, and he came up with the laws of motion, universal gravitation, invented calculus.
Please don't expect that from us.
As long as you don't expect that from me, we'll be good. What were we going to say, Andy?
I just pulled up the COVID things. There's 200 new cases in the U.S. since yesterday and 6 more deaths.
And we're sending a whole choir group to California.
Woo!
Which is declared a state of emergency.
There's
Send it on
two
the
us in California.
Good luck.
Yeah, well, I don't want to get too sidetracked on it. There is reason to be concerned, but there's not reason to panic.
But should we be sending students on a bus to California?
Literally, they're not gonna let us come back
Okay.
to school.
I'm just saying.
This is off topic, but it's very topical otherwise. What are the chances that you will get the coronavirus?
There's more.
You know what? It's a lot harder for me when I work in a hospital.
Yeah, but like we're gonna be like, hold up, this is a problem. Like we have to look at it because like because coronavirus, like everybody's gotten the coronavirus. This is just like the specific strain. Because like coronavirus is like the cold and flu.
I never had. I didn't think the flu was a coronavirus. SARS and MERS were, but
Coronavirus is like an
SARS.
It's an umbrella. It's an umbrella.
the coronavirus is SARS and
virus.
MERS. I mean, SARS, MERS, and this one are all coronaviruses. But I
Yeah,
don't think
it's
flu
just
was.
a new strain. This is just a new strain. Because like coronavirus is like an umbrella term for like the flu and the cold. And so like the problem, like because a lot of people are like.
So we should really be calling this novel virus rather than coronavirus.
Yeah, well that's why it's more.
Although
accurate.
SARS and MERS were novel coronaviruses.
Yeah, it's more accurate to just call it COVID-19 because that's exactly what it is. But like,
Well,
the
that's
thing-
its name.
but like this, like the thing is that like people are comparing it to Ebola, and like the thing is like with Ebola, like, no, you weren't gonna get Ebola, but if you got it, you would die.
Yeah.
But like with COVID-19, like we're probably fine because like everybody could
You
get
speak
it.
for yourself.
Well, here's the thing, because like. we're
I heard the same. Go ahead, Ms. Bauer.
Yeah, so we're correct. Okay, guys.
Well, because like it's so easily spread that it's more likely that everybody's gonna get it, and so but it's more dangerous for vulnerable populations, which is why like I would be fine if I get it. I'm probably not gonna die before I get hospitalized, but I'm gonna prevent getting it myself, so I can prevent giving it to somebody who would die. Because like the people who are gonna die are the elderly and people with respiratory illnesses and probably poor people because they
How do you
always.
do this stuff? Which is, am I jumping?
You have to look on the CDC.
Yeah.
I've been like listening to podcasts and stuff like that too, and like the WHO like has all this stuff, and there's a lot of
Everything, yeah, everything Claudia just said agrees with everything I read from the CDC website.
Not just this is great.
I want to be funny and say, but how do you know you can trust them? I do too.
Yeah.
I've been
because they
reading.
make mistakes too.
I've been trying to read up a lot about it. And of course, what you're saying now, who's vulnerable? We probably will all get it. That's what I think.
Yeah.
But will you even know you had it?
Probably not. I probably
You
already
guys may not know you had it. Me, having a quarter of my lungs dead, I'm sure I'll have a big reaction when I get it just because of that.
So, man, how do you do it?
We're all probably gonna get it. It's like the cold, like it's hard to keep that spread.
Yeah.
That's why
Everybody
you
gets
send out
cold.
emails
But the thing is,
about
the
it
reason-
to the school, like wash your hands and everything.
I was like, I'm worried about
dying.
cleaning our computer keyboards, but not the desks.
The reason that people have been asked to put so much effort into like fighting the spread isn't just because like it's like a bad case of flu, right? It's because like the vulnerable populations are very vulnerable. 17 of the 28 deaths we've had in the US were one nursing home
Yeah.
because it spread among everyone there, and almost everyone who got it died in the United States.
So we're
Like
good.
a doctor.
Like
Yeah,
to
you're
be
good. We're good.
but you should stay safe so that you can keep other people safe.
Yeah, and there's like a 5-day incubation period, so like if you're exposed to it and if you're incubating it, like everyone you see in 5 days, if you see your grandma in 5 days, or
Well, I
your
thought-
grandparents, like,
I thought you can't tell the difference.
or if you like volunteer or anything. Well,
When you
like,
get tested for
Max, you could get it and you wouldn't even know.
Yeah.
Let's say I have the flu, right? I flew like, you go to the hospital, they can't tell you.
No, well,
Yes, they can. They have tests. Literally,
They're
that's
testing.
why there's some. Because I work as a phlebotomist at Bryant, and when you have like a suspected problem or whatever, you're supposed to use like a PAPR. The only time that they use PAPRs is like for TB, and it's so rare. So I've used like a PAPR like 2 times in the whole time I've been a phlebotomist, which is like just about a year now. And this like last Sunday, I had to wear it for like 6 to 8, patients because they were suspected. Because as soon as they hear that they've been out of the country or they have like certain things that they're gonna do the actual test on it. So there's like an actual test that they do, and then they take extreme precautions, and you get totally suited up for probably nothing.
That's what
But
you
they
do.
they just test it. So in the ER, that's what's happening right now. There's like lots of people going in and getting tested for like mild illnesses that they think could be this.
Yeah, we shouldn't be weird.
no.
No.
You can also get, now they have like commercial testing kits available too.
One of my childhood friends is a professor at the University of Rome. And of course, you know that the entire country of Italy is now quarantined, right? And so if you have symptoms, you're supposed to stay home, if you have fever or cough. And if you have multiple symptoms, then you call a hotline number and you tell them what your symptoms are. Based on what you tell them, they may, if they think you might have, they'll send somebody to your house to test you. That's what they're doing in Italy.
I just think it's interesting because like the countries, to me, just like because I think global health is so interesting from like studying stuff. The countries that are struggling the most with the most spread, it is kind of the worst. Like, so they, well, not the worst, but like they have very weak healthcare systems, and like, so like we're probably gonna be fine because we're in the U.S. and like the U.S. has like a pretty decent like it just has like a really decent like setup and stuff like that. So if something happens, even though we're not that prepared, like we have things in place to be prepared. So like it's just kind of sad because like it goes back to like who's gonna suffer, like people who live in poor countries who like won't have these preventative measures and stuff like
Like
that.
people in Iran.
Yeah, like they have like lower quality of life anyways, and so they're gonna suffer more.
And if you looked at the statistics, if you're under the age of 50, based on the Chinese data, where they smoke a lot more and so there's more danger there, your odds of dying are something like 0.2, 0.3%. But if you're me, even without my lung issue, without being male, it jumps up to 1.3%. If you're a male, it goes almost twice that. If you're a girl, it drops to about half that.
Wow, you call it.
So, those of us are guys, it's
Well, it's not
we're so, right?
You know what I'm saying? Good to see you.
Who are you gonna sue? The
The
virus?
CEO of
The
Coronavirus.
virus?
Yes.
So from 50 to 59 is like 1.3% die. And then it just goes up. So the people over 80 is 15%.
I know, I find that just ridiculous and stupid. Are people really that stupid?
Yes, they are.
He said that if it was across the entire world, 2% of the population would be projected to die, which is like a huge.
That's a cheat code.
I have a student who said that never came wrong. There's a certain amount of.
Let's do it.
See, just thinks I should be able to- Okay, so I don't know. We should have gotten all off topic on that, but it's something that's very topical. It's not physics, but it's science.
Wait, I just have one other question though. If they did shut down the school, how long would it be shut down for?
The way that this is spreading, it should be done by the beginning of next school year, I believe.
Would they keep us shut down for the rest of the school year?
That's what I would suggest, yeah, because it's growing. You're not going to like, oh, we shut it down now, but now that it's 3 times a bigger problem, let's all come back together. That's not the way it's likely to work.
That is ridiculous. How would people graduate?
Yeah, there's a lot. Yes. Ms. Bowers?
Just like a side note on that, I was listening to like this
There's no one in
thing,
Nebraska.
and this person was like comparing it to when the Spanish flu came in like 1912, yeah, 19 somewhere around there.
I'm scared.
And they said that like the U.S., the first wave, the U.S. responded because it happened like in the springtime. The first wave responded in the summertime. It went away because viruses don't really survive very well in warm weather. But then it was the second wave in the fall that killed so many.
Crushing.
Yeah, they're doing that that you could finish.
Because you probably had a lot of it that was now spread out.
Exactly. So they all just got like certificates for.
No, no, we will not do
Yeah, I
that.
got trouble.
No, I just
That would bankrupt the college.
There's no way.
Because there's something you got to do something.
No, because it would just like be an incomplete until you came the next school year and finished it.
There's no way.
That's what's happening at.
Do what?
There would be some
That's
courses
true.
that you
That's
you
true.
couldn't like
EMT.
EMT they couldn't
Roll
finish.
the grease.
But most classes you could just transfer over, so you just have it incomplete until you finish it, so you wouldn't get your money back.
Yeah,
You
I don't know what they're doing, but I know that we can't give people their money back. We don't have that kind of money back.
That's stressful.
That's stupid. I hope that this no. I think it's
Okay,
I think they're really bad about this, that there's a chance.
well, everybody's talking about it. It's like the government told us we have to talk about it.
Are other Adventist colleges thinking about doing it too?
All colleges in the U.S. should be having this conversation.
UNL's having that conversation.
You were a little popular though.
I know.
Well, they're talking about moving toward entirely online.
Yeah.
So like my teacher's talking about like if we do go online, like this is how she'll have to set up. One of my like kids here already made an online class. Like we're all.
I'm pretty sure Midland University shut down, aren't they? Midland?
Yes, I think so. I think that was one of them.
Yeah.
I get rigid lost.
Okay, well, let's finish my little lecture so we can do you can do your experiment. So, one more. I haven't given you any clue to the answer for this. This is your preconceived notion. Why is the sky blue? Max?
Philosophy.
Sky's philosophy.
I literally hate it.
Is it? Some people say it's because it's reflection. Yeah. What? No. I think that's wrong. That's wrong because in the bathtub it's also blue. And the sky ain't in my house.
Okay. So far I have no answers. There we go. One.
I'm gonna guess that one.
That one.
And by the way, I want you to know everything on here is a factual thing. They're just not all reasons why the sky is blue. Okay. Okay, start it over. Start it over for you. Okay. Here we go. Max had to get his answer in. I wasn't going to tell people that, Max. Okay, there we go. Apparently it allowed you to select more than one so Sarah could answer all of them. Water obviously reflects sunlight, but that's not it. Water in the atmosphere absorbs more red than blue. That's true, but that's not it.
Wait, why would you put a true thing in there?
They're all true, but they're not why the sky is blue.
What was the answer?
D is correct. Me scattering. Me
What does it
scattering.
mean?
Yes, what is me? Was a Chinese physicist. Me scattering is light that hits particles that are bigger than the wavelength of light. And when light hits particles that are bigger than the wavelength of light, like water droplets, then the light is scattered in all directions equally. So when you look at a cloud, if it's a thin cloud, you see the color of the sun. What color is the thin cloud?
It'd be kind of yellowish. No.
What color is a thin cloud? White. That's the color of the sun.
No.
Yes, it is.
Look at my kindergarten girl. Yeah.
You're right. You in kindergarten knew. So then we get to D. Rayleigh scattering strength is proportional to 1 over wavelength to the 4th power. So blue is scattered a lot more than red. So just imagine this. You have the sun in the sky, this big white ball. So here's the sun.
It's not white.
You are standing here. Light from the sun comes and it hits the Earth's atmosphere, and you have a bunch of blue light that goes off to the side. If you take white light and you remove blue, what color do you get? Yellow. And so what comes to your eyeball looks yellow. But if you look out this direction, then you're going to see light from the sky, the sun that came like this and then was scattered, and so you're going to see blue. So when you look toward the sun, you see the sun minus some blue. Not minus all of it, minus a small fraction. But that's what makes it look yellower than it really is. If you look any direction other than the sun, you're only seeing light that was scattered by atmospheric particles, which are smaller than the wavelength of light. Rayleigh scattering is what occurs when you have scatterings that are smaller than the wavelength of light. And so you're seeing primarily blue. And when you look at cloud, because you have scattering off of bigger things, you have all of the colors mixed back together, giving you back the white. Learn something?
Yeah.
Ish. Okay. This is just to show you water absorption. Water absorbs less blue, more red. And so that's why if you have a deep water, it will take on a blue color because you have more red absorbed than blue. Also note that water absorbs a lot here in the range of wavelengths that are longer than visible. We call that infrared. That's important because the greenhouse effect. Visible light largely gets through the atmosphere, but the Earth gives off light that's mostly infrared, and that's mostly absorbed by water in the atmosphere. So our greenhouse effect is primarily driven by water in the atmosphere. Now, there's other gases that contribute to the greenhouse effect, and one of the very weak ones is carbon dioxide. We always talk about carbon dioxide, because it's one that man is very responsible for, whereas the water in the atmosphere, we're not very responsible for. So we don't talk about that, even though it's the primary one. Rainbows, this is the last topic. Rainbows are caused by light reflecting off of the inside of droplets of water. So you have a first and second order rainbow. The first order rainbow is the one that's caused by light that comes in, goes into the water. English, blame it on the coronavirus. Water has a different light speed depending on the color. We call it a dispersive medium because the light speed is different based on color. Hence, the colors will separate when they go into water. They will refract at different angles. And so when the light goes into the water droplet, and you can see it a little bit in this diagram there. The two extremes, the violet and the red, separate. The violet bends more because the violet light goes slower through water than red light does. Then it hits the back and reflects. Because of that reflection, the violet and red cross over each other after the reflection. and then the refract coming out. And the result of that is you have red light and violet light coming at you at different angles. And so when you see a rainbow, you have a whole bunch of water droplets like this in the sky. You have sunlight hitting them like this, and you're standing over here, and you are going to see the one that's flatter, which is, let me actually change to blue. You're going to see the blue one. That was supposed to be blue. That looked black. Blue. There, that'll look blue. You see the blue coming at you like this, and you see the red coming at you at a steeper angle. So you see the red above and the blue below. So the blue is on the inside of the rainbow. The red is on the outside for the first order bow because of the light red versus blue bending different amounts. And the colors in between bend by the values in between as well. Second order bow is two reflections in the raindrop. So light comes in, separates, one reflection crosses over, reflects again, comes out, crosses over, has two crossings. That reverses the order. So the second order bow is like this. So this is the second order, and this is the first order. Good contrast there, blue on blue. So has anybody seen a double rainbow? You have the double rainbow because you have first order like this, second order like this. My first year teaching, I only talked about the first order rainbow. And the MCAT that year, they had a question about the second order rainbow. I felt dumb that I hadn't talked about both. So that's why I make sure I always talk about both first order and second order. So here's a picture showing the first order rainbow. Notice the difference between this region and this region. You see the difference? Verbalize it. What's the difference there?
One is considerably more blue.
That seems like the right answer, but it's actually slightly different. This here has extra white. This one doesn't. So it looks more blue because it was generally a blue background. Right? So that's why that seemed like a right answer. But it's actually the extra white. You're having some backscatter meaning light coming back at you, from the droplets inside of that first order bow. Outside the first order bow, all of the light that is being interacting with those droplets is going away from you at the end. It's not coming back toward you. So you basically don't have any light coming back at you that originated with the sun, and so you see what's in the far distance. That region, by the way, is called Alexander's dark band. No. But it's physics. It's very interesting. Or as my teacher said, remember, it's not Alexander's ragtime band. He was very funny. Here you can see the first order bow, the second order bow. So here's the first, here's the second, and here's the dark band in between. Dark because you don't have that white light coming out at you. So second order bow is roughly 51 degrees. That's measured from the sun is back here. Got to change color since I'm no longer in that. So the sun is back here. The angle from the direction your shadow would go to the direction where the rainbow is what we measure for these. First order bow about 42 degrees. Second order bow about 51 degrees. I have one more woo clap question, and then we shall do lab. What color is on the inside of the first order rainbow? Purple is not listed here. Oh, I don't know what you answered.
Oh.
But there are some wrong ones. All righty. Well, you shouldn't have shame. You're putting down what you think, right? Is there any shame to thinking, even if it's wrong? So there's the answers we got. The plurality is correct. Violet or blue. Now, I want to go back. 2 people said white and 1 person said black. I want to go back a whole bunch of slides to the eyes, rods, and cones. And we're going to stop when I stop talking about this graph. Red, green, and blue are the primary colors. The colors you see in the rainbow are all of the pure colors. Single wavelength produces those. And we generally talk about Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. My brain says these are all blue. But that's my brain. It's just, I can see that there's a difference. Then we had those secondary colors, the primary pigments, cyan, yellow, and magenta. Yellow is here in the pure colors, but it's also what we get when we mix green and blue. So what about white and black? White is what we perceive when we see roughly equal amounts of all of the colors. In fact, the standard for white is called D65. What does that mean? That's the color you see when you look at a filament in a light bulb that's at 6,500 kelvins. The sun is about 6,000 kelvins. So that's pretty close to the color of the sun is what we consider the standard for white. So white is seeing roughly even amounts of all of the colors. What about black? Black is simply no color. That's what was being shown here. A black object just simply reflected nothing. So there is a fabric, I can't remember the name of it now.
Oh, Vanta?
Yeah, Vanta black, that it reflects less than like 0.5% or something of any light that hits it. So it really, really is black. And it's pretty crazy. So black is no light at all. White is equal amounts of all the colors. What about purple? When I was a kid and we had our Crayola crayons, we had purple and violet and magenta, and I could never tell them apart. You know why? Even though technically there's a difference between magenta, I believe purple and magenta might be the same thing. But there's a difference between magenta and violet. To the eye, there's not. Violet is when you have light right there. Now, if you look at that, according to this picture, that would only be activating blue, right? So that's how we perceive violet. But there is a little bit of green and red there. And if you had something that was a combination of red and blue here, you can get the same percentages of red, green, and blue cone activation as you do with pure violet. And so a purple can look just like violet, but it's made up of different colors that are activating the same amounts of cones. Now, in preparing for today's lecture, I was looking at anomalous color things, and there are some people with a condition where they don't have a cornea, actually, I think it said. The cornea absorbs ultraviolet light. We could see ultraviolet if it wasn't for the cornea. And so those people can see ultraviolet light. And the ultraviolet light looks generally white to them. Why generally white? Because the red and green tip up a little down here in the ultraviolet. And so you're getting pretty equal amounts of red, green, and blue activation if you actually had ultraviolet going through your cornea. Which is really cool. Okay, I am done lecturing. what you're doing for lab,